Okay, so this is the equation as per se. This is what we have right now. Thing is, we also need to break this down into different areas or domains, different elements, like the finite element method. So we need elements. So in yes, elements. So in 1D, it's fairly easy. Could have just regular sampling. That's the same as finite difference, though. But say you have some kind of different parameters that say that that necessitates you to actually have a finer grid in one area. For example, for instance, in the middle, then you can have a lot of smaller there, and in the ends you have larger grid sizes. All this 1, 2, 3, und so weiter. G and -1, E -1, and as the last one. Okay, so that's in 1D. That's fairly simple. There you can also order them in a pretty easy manner because, well, this is first and then it goes to the right. In 2D, it's a bit harder to keep track of. Say you have a model that looks like so. Okay, for some reason this is your model. Doing this in finite difference, you will need to use the full space. But in finite elements, you can be constrained to just this small model. Okay, but we also need to decompose it. Have an element here. This region, we have more elements, and so on. Let's see. So this is just arbitrarily elements. So number them G1, 2, G3, 4, 5, 6, 7, just arbitrarily. The thing is here that all of these domains should be disjoint, meaning that they don't overlap. And these are called the elements. So in fancy mathematical notation, we'll say that the union of all the elements, so we have NE, that's the amount of elements of these, are just the domain G for full. Oh yeah, this is just a repeat of what we had earlier. So I'm just covering this. And also, if you have two different elements in here, the what's this in English though? The the snit, the snit, the overlap of them, to put it bluntly, is the empty set. This is just a fancy way of writing that. Okay, if you take the union of all of the elements, so if you put all of the elements together, like you glue them together, then you get your full domain, but none of the domains overlap. That's what this means. It's like set theory. Again, this is for all I equal j. Because of course, the overlap with element 1 and itself is element 1. So, yeah. Okay, so what we have to do now, we have to solve this equation, weak formulation, on each and every of the elements. So we need to also sum over the disjoint elements of our domain. There's going to be more sums. So you can compare with the one to the left now. We'll get not a lot. One, try to make the brackets this time. I of t, then we need sum 1 e o j c I x plus sum of all the basis elements n I e, and then we need all of the elements again, e equals 1 e mu dx c j dx c I dx equals, we have to do the same with the source function, b equals 1 and e c j f dx. Okay. The problem here is this u of it, that's over all of the the domain. So we need to decouple them. We need to kind of decouple all of the elements. So okay, so these, they are all over all of the elements, the ui of t. dy. These are temporal coefficients that are that I depend on all the integrals over all of the elements. So we want to clear them out, so we don't have to do this sum for all of the elements in order to find these. What we do then is kind of the trick. That is to introduce these basis functions that only have support on one element. So each element could have as many basis function. No, each element could have, how to say this? Each basis function have support on only one of the elements, but each element can have support from more than one basis function. Does that make sense? Okay, so to illustrate the idea here, say that you have only two, let's say 3 intervals, like this. Okay. So you want one basis function that has support on only the first one, and it's 0 the rest. The next one should have only support on the second one, and the third one, well, it's 0 on all but 1. And then you can also have more basis functions, but each basis function should only have support on one element at a time. So I can introduce one more basis function, which has more support than the first one here, and then it's just 0. So you can express each basis element using more basis functions. Okay? So when you do this, you can decouple the sum and the integral. So you only need to solve it for one element at a time. Okay? You kind of get different basis functions for each element, and then we can solve this as, well, discrete equations. They aren't coupled. Meaning that in order to continue, we can focus on just one element. So I'll define Okay. One. I'm being lazy, so ELT element. Okay, so on this one element, we will define n plus 1 basis functions. Funks, we'll call this C, I, E. Okay, on each of the elements. Okay, so each element has the same amount of basis functions, and which basis function it has support on is defined by this number E. So there's a lot of bookkeeping here. Then have that the displacement inside element GE inside GE, because now we can actually decouple them, going or approximated by U bar of T, where X inside this element GE. And you might think this is very complicated for just a 1D case, but it also generalizes for higher dimensions. One, as some motivation, I mentioned that it was the Leipner was one of these oil platforms of Norway. It failed because the engineers that built it, they didn't understand the spectral element method. It basically just failed because they didn't know how to use tools they were given. So they used too coarse of a grid with finite element method. So that's why we go through this. U, I, at the element E, function function T, of course, C, E, D, I, E, X. Okay, and then we have to rewrite, or not rewrite, but refine the weak solution yet again. Okay, so now we can actually remove this sum here, because now we're only looking at one element. Plus 1 and 1 I function E, creating E, rho C J C I dx plus I plus 1 plus 1 U I E T G E mu dx C J dx C I dx. E T f of x dx. Okay. Again, have matrix formulation of this T A E at T f of E the local mass matrix. So we are kind of splitting the problem into the big problem of the whole domain into smaller problems on each domain. And the smaller problems should have a more accurate solution than the bigger problem. Stiffness. And okay, so then we have the million-dollar question: how many basis functions do we have now? So each element has n plus 1 basis functions, and we have how many elements? Ne. So in total, we need Ne times big N, or capital N plus 1 basis functions. Different basis functions. And also we have a slight problem. Well, not slight problem, it's just something you have to keep in mind. That is that each of the basis functions, they only have local support on one element. But our wave field should be continuous. So we have to impose this continuity of the wave field. That it's transferred properly from one element to the other element. There has to be some kind of continuity there. If not, then suddenly the wave could go, well, say you have displacement going so, and you've done something wrong with your calculations, well, maybe it starts up here. And then, I mean, the weak solution allows it, but it's not really physical in our case right now. Shouldn't have this jump here. Displacement. I mean, you could have it, but not always. Yeah. Okay, we also have one more problem. Now we have to solve it for each and every element. Each and every element is different. What if we could map each of the elements into some kind of master element? So we can just use some kind of simple transform and save a lot of computation time. So that's what we're going to do next. We're going to introduce a so-called reference element. The same we did with the, was it the Gaussian quadrature? With the GL points, Gauss-Legendre points, integration. Then we also had some kind of reference element. So we're going to use the same trick now, or a similar trick. Okay, so again, you can see this is easy to do in 1D, because we can basically just scale all of them. If you just scale all of them in a proper way, or maybe shift them, then they will all have the same size. but we need this transform for each of the elements. This also saves us a lot of basis functions. A reference element. Okay, so in X space, our interval goes from A, B. So this is the GE element in X, and we want a transform, which I'll call FE inverse, going this way from -1, 1. Call this element big lambda in the size space, and going back, have FE. Don't see this enough. So basically, FE here is a transformation from -1 +1 into, well, GE, such that going from each of the spaces, so psi of a kind of x as the inverse of. This is basically just using this function fe to go between the spaces. It's either the forward function or the backward. So I want to find a linear mapping from our kind of real space into reference space. Then also use it back, the linear mapping. So again, fancy terms, bijective. So each element here should have one corresponding point here, or each point in X space should have a corresponding point in size space, or reference space. How do you do this? Okay, so start with. So I'm just going to make a small detour, but doing the calculation is a bit easier. So first, I will only look at mapping one half of it. So this big lambda bar was 0 to 1, and we'll call omega, capital omega, whole space from A, B. So on in this reference space, we want a function u of e. We approximate it such that the endpoints match up at least. So we have u of e equals c1 plus psi, such that of 0, c1 of 1 equals 1 plus e. What we want to map. Okay. Now we need to find expressions for C1 and C2, and we do kind of that. Two equations. So, basically, C1 is U of 0, 2 of 1, 0. So shall we have or transform? It falls out, i.e. that's 0, 1, 0, times e. And now we can do a transformation of the basis function. Oh, okay, I got a detail. Now we only have basis functions, the space. And first basis function and 1, C, E, second one, and 2 is just E. Those are the basis functions we have right now. So now we only have 2 basis functions. But the thing is, these are basis functions for this space. But if I just say that moving from to lambda, we can just use transform plus 1 divided by 2, such that basis functions in reference space going to be 1/2 minus E 2 s 1/2 1 plus psi. Now only 2. Okay. And using these 2 basis functions, we can figure out or transform Fe by looking at the endpoints. In this case, F from reference space into real space, A over 2 minus psi, B over 2, 1 over C. Okay, similar to the integration, Gaussian quadrature. So now we can soon do this on the reference element and then just map it back and forth. Okay. Okay, using this. So using this transformation, get, because we want to do integration here, get the C dx d c I psi over x. Or we don't really use the transformation there, but is this correct? What have I done here? I've just multiplied by 1, basically. Plus psi dx equals psi over dx times psi d psi. And then this is notation abuse, but you can just these. If any mathematicians were in the room, I would get a beating for saying that, but it works. Okay, and then we are back to our weak form of the wave equation. We're going to use this transform. So bear with me for 10 more minutes. So we have basis functions. Now we have big N1. Still only on one element. Minus 1, 1. Row. We need to transform all the model parameters as well. That's just basically a remapping. E x phi I e x phi d phi e. Okay, so where does this come from? That's the same as here. And then the same trick for the rest of the terms. N plus 1 I e prime minus 1, 1 psi I e x psi psi dx squared dx psi. It's 1 to 1 psi e. Do the transformation of this thing as well. F of psi psi. Yes, it's starts getting complicated. So next, we're finally going to pick basis function. It's exam relevant. The thing is, it looks very advanced, but just sit down, try to look at it. I actually recommend this book here, the one I linked in Slack. It's available for free as long as you're connected to the NTNU Wi-Fi. Download it, PDF. It's what I'm lecturing now is chapter 4. And yes, this has been on the exam. Additional book? Oh, yes, chapter 4 of this. Yes. And also, you don't have the whole book, part of it. Okay. Basis functions, basis functions. This is the fun part. Okay, so as I mentioned, we can use whichever basis functions we want, but if we are smart about it, we can get some basis functions that makes all this pain go away. So we'll do Lagrange polynomials again. Okay. So we choose n+1 Lagrange polynomials with um, so-called Gauss plateau Legendre points. GLL points. Oops. Co-location points. Okay, so earlier when we did interpolation, we had Gauss-Legendre points. Okay, so this is some repetition. Say we have some kind of interval here, kind of our basis element. Do it like this. Okay, so the GL or Gauss-Legendre points, they were always inside here in order to get, this is integration. So the GL points, they were always inside to get a better quadrature of your, while you're doing Gaussian quadrature, you had some GL points, and they were always inside the interval, okay? These Gauss-Legendre points, they're based on the same principles, only that you force two of the points to be on the edges. There you have 3 points there. there, so that's GL points, and blue ones are GLL points. And the reason why we want to force also using the endpoints is for this continuity thing. We want the field to match up at the ends. That's why we need these co-location points or interpolation points, if you want, at the end of the intervals. I will not write a table of them, but you can find them either either online or as a table in this book, or in the formula sheet of the exam. Anyway, we pick these such that Ci of psi Li minus 1, 2, 1. Okay, so again, DLL points, they will suppress Runge's phenomena. Yeah, Li, because it's Lagrange polynomials. Just one more equation, need to go. Again, sum over all the basis functions, I double E of E plus 1, row tilde I, Li, xi, x, tx plus equals 1 plus 1 ui e of e minus 1 u e d a I by x squared dx d I dx. Then I guess to run finale tomorrow. I dx xi. And you see this is basically the function we had, only the size are switched out with the Li's and Lj's. And also this tilde, that's just shorthand for, well, we're evaluating it at different places. Or we're doing a transform, so Go. Go. X of X of this. Questions? I'll do a short recap tomorrow of everything we've gone through, because I know this is a lot of details. But it all clears up in the end. I hope it pays off. Neste uke.